In the last video, we discussed tension in static applications, meaning the objects aren't moving. Now we'll discuss tension in dynamic applications, meaning objects are moving and maybe accelerating. First, let me point out that all of the rules discussed in the previous video on tension still apply, and will follow the same basic procedure to solve problems, which was to apply Newton's second law. The big difference this time is that the acceleration of the objects may not be zero. One more thing we'll do in this video is to go over a technique that can greatly simplify tension problems with multiple objects. Let's start by looking at a simple scenario to compare static and dynamic problems. In this scenario, a 5 kilogram mass is suspended motionless from a wire, and we want to find the tension in the wire. Let's quickly go through the solution. Here is a drawing of the scenario, and now we'll draw a force diagram and define the coordinate scheme. Next, we'll apply Newton's second law in the y direction, and then recognize that the acceleration is zero, and applying the values for m and g, we get that the tension is equal to the weight of the object, which is 49 newtons. Now we'll change the scenario. This time the 5 kilogram mass is pulled up by the wire so that it has an upward acceleration of 2 meters per second squared. What is the tension in the wire this time? Here's the force diagram and coordinate scheme. And this time I'll add a vector showing the acceleration. Now let's apply Newton's second law again in the y direction and solve it for tension. The key difference this time is that the acceleration is not zero, so we leave it in and plug in values, which gives us a tension of 59 newtons. This time the tension is greater than the weight of the block, which is 49 newtons. If you think about it, it's logical for the tension force to be greater than the gravitational force in this situation. Since the block is accelerating up, then the net force on the block must also be pointing up. That in turn means that the upward tension force must be greater than the downward gravitational force. That's why, by the way, that I drew the tension force vector longer than the gravitational force vector. I knew that it had to be that way for the block to accelerate up. Now I'll work through a more complicated scenario that involves two objects. I'll apply the simplification technique that I referred to earlier in the video. Here's the new problem. In the picture below, block 1, which is 8 kilograms, is attached to block 2, which is 4 kilograms, by a string. Block 1 is placed on the table and block 2 hangs over the side of the table. The string goes over a frictionless and massless pulley. If the friction between block 1 and the table is also neglected, what is the acceleration of the block and the tension in the string? Let's start by doing a force diagram of each block. For block 1, the string and the table are in contact with the block, so there's a tension force and a normal force, and then there's a gravitational force as well. For block 2, the only contact force is the string, so we have this tension force, and then there's the force of gravity on the block. The other detail that is useful to add to the diagram is the direction of the acceleration for each block, which logically would be like this, because the hanging block pulls both blocks in that direction. Notice that the magnitude of the acceleration for both blocks is the same, because they're tied together by the string. The next steps are to define the coordinate scheme, apply Newton's second law to each block, and then solve the equations for the unknowns. But there's a complication. If we define the coordinate scheme in the usual way, like this, the math turns out to be pretty tricky, because the acceleration for block 1 is in the positive x direction, and the acceleration for block 2 is in the negative y direction. This causes even seasoned professionals to make mistakes. To make this more doable, I propose the following procedure. The procedure itself may sound confusing at first, but bear with me. Ultimately, I think it makes a problem like this easier. So what we're going to do next is to define a different coordinate scheme for each block, like this. That way, the acceleration of both blocks is in the positive x direction. One way to think about it is that we've defined an x-axis that follows the string around like this. At this point, we could write down Newton's second law for each block and solve the equations, but I like to carry the simplification a little further. The next thing I'll do is to redraw the picture so that the x-axis is in a straight line, and I'll do that by rotating block 2 and lining it up with block 1. To show you what I mean, let me remove everything except the blocks and the forces, and now I'll rotate block 2 like this. So we started here and then rotated here. One more time, we started here and then we rotated it counterclockwise up to here. Notice that all of the forces were rotated counterclockwise with the block. Now that we've stretched the string and the blocks into a straight line, both blocks are now accelerating to the right, and they share exactly the same coordinate scheme shown here. This modified picture is mathematically the same as the original picture, but it's easier to view and apply the equations to. Now at this stage, some people like to finally apply the equations to each block and solve for the unknowns. But there's even one more simplification that I recommend. That is to define the system to be both blocks combined. So that means that we define the system to be this, and all of the forces are now combined, which means that the two tension forces in this problem cancel, and there's no need to show them any longer. As a result, the diagram simplifies to this, or if you like, you can make it physically smaller just to clean up the picture a little bit. In addition to combining all of the forces, the masses are combined as well. So the mass of the combined system is 8 kilograms plus 4 kilograms, or 12 kilograms. Now finally, I will apply Newton's second law to this system. Here is Newton's second law in the x direction. We can see from the force diagram that the only force in the x direction is the gravitational force on block 2, or m2 times g. Keep in mind that the mass on the right side of the equation is the mass of the entire system, so I'll make it m total to keep it straight. And then, solving this equation for the acceleration, we get this. And plugging in values, the acceleration is 3.3 meters per second squared. So there's the answer to one of the questions. To find the tension, we can go back to the previous picture before the objects were combined. Using this picture, we can define either one of the objects to be the system and apply Newton's second law to it. I'll make block 1 the system, and then I'll apply Newton's second law in the x direction. There's only one force in the x direction on block 1, which is the tension force, so that the equation becomes this. Notice this time I made the mass on the right side of the equation m1, because we defined the system to be object 1, so we just want to use that mass. Since we already found the acceleration, we can now plug in values, and we find that the tension is 26 newtons. If we had defined the system to be block 2 instead, then we still would have found that the tension is 26 newtons. I'll leave this to you to try out. As I mentioned, this process might seem cumbersome at first, but it can actually be done fairly quickly, and it makes it much less likely to make a math error. There's an example on Moodle that works through 3 scenarios of varying difficulty, so I recommend that you view that video as well. And that brings us to the end of this video.